Okay, let's start. Problem set 10 due Tuesday, 6 o'clock. So for the viewers at home, all of these will be done. The one thing that has changed, excuse me, the necessary factor is that the density of the material in that cube is 1,400 kilograms per cubic meter. So that's the correction. Now on to the problems. Problem 1, 100 kilogram hollow sphere is neutrally buoyant. Stop. So we have a 100 kilogram neutral sphere. It is neutrally buoyant. So sum of the forces in y is equal to 0. It's submerged. The mass of the sphere in gravity, mass of the sphere is 100 kilograms. Its volume is half a cubic meter. So volume is 0.5 cubic meter. If the space is filled with a combination of water and helium, what fraction of this volume is helium? So volume of helium over total volume is the same as 1 minus the volume of water divided by volume. So anything not water is helium. So if you know that fraction of water, you can get the helium. The density of helium is significantly less than the density of water. So what we're going to do is we're going to say that the density of helium is equal to 0. And we discussed our reasoning behind this back on Thursday. So if you don't worry about it, you have three forces: the buoyant force up, the mass of the water inside times gravity, and then the mass of the shell times gravity inside as well. It's neutrally buoyant, so we get to use this. So 0 is equal to buoyant force minus mass of the shell, gravity, minus mass of the water, gravity. Now the buoyant force, density of the fluid displaced or water, the volume, that's given, and then G. The mass of the shell has been given, but the mass of the water has not. Using our density is mass over volume. The mass of the water is equal to the volume of the water times the density of the water. Now all of these G's cancel out. There's one in each term. Now I have to solve for only V sub W. V sub W is equal to rho W V minus MS. Density of water is given. Oh, and when that comes over, that has to come over. MS is given, and then divide by rho W. Volume of the water is equal to the total volume minus mass of the shell divided by density of water. And that will give you the volume of water. And then all you have to do now is plug it in there and to get this. So now we're basically in a plug and chug situation. And that's it for number 1. Manipulating buoyant force to determine helium. Once you find the volume of helium, that mass of the helium is going to be significantly less than the mass of the water and significantly less than the mass of the shell. So much insignificant is it that it's safe to ignore it, which is exactly what we did. If you had a combination of water and milk or water and oil, then yes, you would have to pay attention to it, but not in this case. Water balloon. A balloon is filled with helium and tied to the bottom by a string. The balloon is completely underwater. The balloon's mass is 20 grams and has a volume of 0.4 cubic meters. What is the tension of the string? I believe in this case, this was the demo showing how insignificant helium was. You have the balloon. The buoyant force is up. The mass of the balloon times gravity is down. The mass of the helium times gravity is down. And you have tension, which is down. So sum of the forces is equal to 0, which is equal to buoyant force minus tension minus mass of the balloon times gravity minus mass of the shell times gravity. We're looking for tension. So tension is equal to buoyant force, density of the fluid, volume of the balloon, gravity, minus mass of the balloon times gravity minus mass of the shell times gravity. Mass of the shell was given. Yes?
The first one, I thought was like, this is the volume of water. So I thought we were solving for the fraction of helium.
We are. But what you do is the volume of helium divided by the volume is the fraction. But what we're going to do is we're not going to solve for the volume of helium. We're going to solve for the volume of water. Because 1 minus the volume of water over total volume is the volume of helium.
So we get the water and then we'll put it into that?
Yes.
Oh, okay.
So we have all of this. The one thing that we don't have is, actually this is, I was using B and HE. So this is HE gas. Density is mass over volume. So volume is mass over, I want to get rid of mass completely. So mass of the helium is density times volume. So the tension is rho W Vg minus mass of the balloon times gravity, which was given, minus rho helium volume gravity. And now it's able to be solved. All the knowns are there. Density of water, volume, gravity, mass of the balloon, helium. And I believe if you look at each of these parts, that part will be significantly less than the others if you just look at it from a number perspective. So it's not really those parts, not really necessary.
Do we still have rho of helium being 0 in this one as well?
You could do it either way.
So if that was the case, we just completely like scratch out.
You could scratch, yeah, you could scratch those out. It won't matter. if you included them, it does change the answer, but so small that it gets absorbed by your errors in calculating, using your calculator. All right, number 3. Five cubic meters of an element known as rebellium is lowered into a tank that is filled to the brim with water. The rebellium floats, but 700 gallons of water spills out of the tank. So, volume, 5 cubic meters. The volume of the spill is 700 gallons. First thing that I would want to do is change that to cubic meters. So if anybody can do that real quick. I got 700 gallons. I got 1.9 cubic meters. Let's see. 500 times 4, it's now in quarts, times 946, now it's in milliliters. That's also in cubic centimeters. Cubic centimeters to cubic meters is 100, but it's 100 cubed. So it's 1.892 cubic meters. Well, you could do your conversions at home and confirm that or not.
I think that's for 500.
Oh, for 500? All right, hold on. Yeah, it did say 700.
I got 2.65 for 700 gallons.
2.65, correct. All right, there we go. So that's the volume of the rebellium that spilled over. What fraction of rebellium mass is above the water line? What is the density of the rebellium? So we know that .65 cubic meters is below the water line. That's the displaced water, which means that the volume above is 5 minus 2.65, or 1.35 meters, cubic meters above. So what fraction of the rebellium mass is above the water line? 1.35 divided by 5. What is the density of the rebellium? So you draw your force diagrams.
2.35.
2.35?
That's 5 minus 2.65? Is that where you get the 1.35?
Yeah. 5 minus, this is 2.65.
Okay.
The volume beneath it. So the volume above it is 5 minus 2.65.
Which is 2.35.
Oh, did I do that wrong? All right, big whoop. There we go. Partial credit for everybody.
Well, I was just so confused at first.
Friday afternoon, you are not getting the best. 0.47. All right, before we continue, that's what we're getting, right? So for something like this, it is in equilibrium. The forces up are equal to the forces down. Buoyant force up, mass of the object, gravity down. So sum of the forces is equal to mg, or minus mg, plus rho w vg is equal to 0. So mg is equal to rho w vg. The g's cancel. That m is the mass of the material. Well, density is equal to mass divided by volume. So mass is density times volume. So this becomes the density of rebellium, volume of rebellium. This is density of water. This V here is the volume displaced, not the volume of the object. And that's density of water. So the density of rebellium is density of water, volume of displacement over volume total. And there you go.
Is the water displaced? Is that the amount that's spilled over?
Mm-hmm. Yeah, it's the water that's spilled out. Okay, number 4. An empty barrel is floating halfway in the water. What is its mass? So the mass,
Why would you write the VR just under BB and not under the density?
volume of the rebellion, total volume.
Yeah. But you wouldn't divide it by like the density of water also? Like, you wouldn't divide the density of water by,
No. The density of water is in the numerator. Why? Where would it get moved?
no, I'm just asking why, like, when you divided by the VR, why didn't you put it up, like, the whole thing over like that?
Why didn't I move both of these down there?
No. Like, when you divided by VR, why didn't it go below the density of
Oh, you mean physically? It doesn't matter. I could write it like, I could have written it like that. But with this, oh, this is the question that you're asking? Aesthetics, artistic beauty. I like my students to express themselves in legal mathematical terms. Now, okay, now I'm starting to wake up. Get the anger boiling, yes.
I was just wondering why it was written that way.
No.
If it made a difference.
Huh? She does. Do you have a journal of that wondering? I would love to read it. Why do you park in a driveway but drive in a parkway? I don't understand. These are the things that concern me. All right. Number 4, the barrel. An empty barrel, they give the dimensions, is floating halfway in the water, which means that the volume is twice that the volume of displacement. It says it's floating halfway in the water. The volume of displacement is half that of the total volume. Mass gravity down, buoyant force up. Sum of the forces is equal to 0 minus mg plus FB. So mg is equal to FB. Now mass times gravity, we're looking for mass. The buoyant force is rho water volume of displacement times gravity. The g's canceled. Since the displaced volume is half that of the total, it's rho w pi r squared h over 2. And that's the mass. The volume displaced is half of the total volume. The total volume is pi r squared h. Divide by 2. Ta-da! There you go. All right, number 5. Another balloon. 10 kilogram balloon is filled with helium. Its volumes is 200 cubic meters. How much mass can it carry? Now for something like this, really the question simplifies. You've got a balloon. The mass of the balloon is 10 kilograms. It's filled with helium. Volume is 200 cubic meters. Now, one question that I'll do to answer to clarify things, it is in air. So you will have to know the density of air, look it up, as well as the density of helium, look that up too. Now, what I'm saying here is that how much mass, like additional paint, can you put on that balloon so that it remains neutrally buoyant? So there is the buoyant force of the balloon, there is the mass of the balloon times gravity, and then there is the mass of the paint times gravity, which has been painted on to the balloon to provide additional mass. So the question is, you've got to find the mass of the paint. Sum of the forces vertically is equal to 0. That means that the buoyant force minus mass of the balloon times gravity minus mass of the paint times gravity is equal to 0. I'm looking for mass of the paint, so mass of the paint times gravity, buoyant force, the density of air, volume, gravity, minus mass of the balloon, gravity. All the gravities shut down. Density of air. Oh, one last thing that, one last force that I forgot. The mass of the helium times gravity. If it was a sphere of helium in water, you could ignore the mass of the helium. But because helium and air are not equal, but within range of each other, you do have to pay attention to that. So there is minus mass of the helium times gravity. Minus mass of the helium times gravity, and the gravity still cancels. So the mass of the paint is the density of air times volume minus mass of the balloon, which they give you, minus mass of the helium. They did not give you that, but the density of helium is mass over volume, so density times volume is equal to mass. So this becomes density of helium volume. And there you go. Then solve. Okay, that's number 5.
Mass of helium G, mass of balloon G, and what is the third on the left side? Mass.
This,
Go up, right above it. No, the left, to the left. Yeah, MPG, what does that stand for?
MPG is the mass of the paint. Yes.
Do air and helium share the same volume?
Do what?
Do air and helium share the same volume?
No, the volume inside the balloon is entirely helium. So the exterior air, the air being displaced, is air.
Okay, so in the last part of the setup, when it's got the density of air times the volume.
Well, when I was writing this, I'm just writing generically.
Oh no, the density of air times volume. Did you use it the same volume? Geometry?
Oh, well, this is for buoyant force.
Okay.
Buoyant force merely cares about the fluid being displaced. The fluid displaced is air. That's why the rho is rho sub A. Okie dokie. Oh, not even halfway. Well, we're a third of the way. Number 6. 200 gram mass oscillates on a spring with a frequency of 8 hertz. What is the spring constant? So period for a spring, 2 pi m over k. We're dealing with frequency, so it's 1 over 2 pi k over m. I'm looking to extract k. F squared equals 1 over 4 pi squared k over m. So F squared 4 pi squared m is equal to k. And that is the spring constant. If you double the mass, how would the period change? So if you double the mass here, T prime is equal to 2 pi m prime over k. The only thing that changed is m. Huh?
Would it double as well?
Well, it wouldn't. I'll show you why in just a second. So m prime is just 2m. Let's factor out that square root of 2. Square root of 2, 2 pi square root m over k. That is your original period. So if you doubled the mass, you would only increase the period by a factor of the square root of 2. Now, if you quadruple the mass, yes, you would double the period. For the last part in number 6, if you double gravity, period is constant. Spring pendula are gravity independent. Number 7. You have a simple pendulum with a period of 4 seconds. Its mass is 5 kilograms. What is the length of the period? Obviously, we're on Earth. T is 2 pi L over G. If you have a simple pendulum, we need to know the length. So it's T squared 4 pi squared L over G. So T squared G over 4 pi squared is equal to L. And that's the length of the pendulum. If you doubled the mass, how would the period change? Simple pendulum. Our mass independent, doesn't care. It won't change. If you doubled gravity, how would the period change? Well, if you double gravity, G becomes G prime. Which is 2G. Factor out that square root of 2. And the new period is the old period divided by the square root of 2. So when you do something like this, you write the new equation with anything that's changed in primes, and then you slowly bring the other equation back to determine what factor is in front of the old value. All right, next. To the moon. You have a simple pendulum that's 1.4 meters long and it has 100 gram mass at the end. In Lewis Hall, what is the period of the pendulum? Well, T, 2 pi, square root L over G. G is 10, L is 1.4. There you go, you got it. You take the pendulum to the moon and measure its period again. What is the new period? Well, you use the same thing, but G in this case is 10 over 6. L is still 1/4, or 1.4. Just a plug and chug. Now, number 9. You have a spring pendulum with a spring constant of 200 newtons per meter. It has a 100 gram mass at the end. In Lewis Hall, what is the period of the pendulum? T is 2 pi M over K. You've got K, you've got M. Be sure to put in 0.1 for that M. And then you've got the answer. On the moon, the answer is still the same. It's horrible. So when you got the pendulum on the moon, the spring constant doesn't change. The mass doesn't change. Spring constant is a spring constant, hence the name constant. So that's it for number 9. All right, number 10 is a little bit of a one-dimensional motion problem. But it kind of illustrates that in earthquakes, there are two different types of waves coming out of an earthquake, S waves and P waves, and they travel at different rates. And for the geologists, you're going to study this in future classes. You have an earthquake from one location, and it sends out two types of waves. The P waves move out at 8.5 kilometers per second. The S waves are at 5 kilometers per second. You're down here in Oxford, and the P waves hit 90 seconds before S waves. So you're there, rumbling happens, then it settles out for about 90 seconds, and then you get another set of rumbling. How far away is the earth? Where did it occur? Now, both start at the same location, both end at the same location. We don't know what time it took for S waves to get there. But we do know, or we also don't know, that the time of the P waves, we don't know that as well. So there's still a lot of stuff that we don't know. However, the time of the S waves is equal to the time of the P waves plus 90 seconds. So let's look at each of these waves. Velocity is distance over time. The velocity of the P wave is the distance divided by the time of the P wave. The velocity of the S wave is equal to the distance divided by the time of the P wave plus 90 seconds. And looking at this, I don't know my distance and I don't know my time of P. But I do know the two velocities of the S and the P wave, and I know the time difference. It's a two equation, two unknown. What I'm going to do is, I'm going to get rid of time of P because I don't really care. I'm not looking for it. Move that up there, and the time of the P wave is distance divided by the velocity of the P wave. So Vs is equal to d. Tp is d divided by Vp plus 90. So now I have one equation where there's only one unknown, and that is the d. So let's do some algebra and extract the d. I'm going to bring that up. I'm going to bring that down. I'm going to move this over here. I'm going to factor out the D. I'm going to move that down. And that gives me the distance. So now you can just plug and play. VS is 5, VP is 8.5, and then you got 90 up top. And then that's all you need to know for that. So it's set up and it's a little bit of unusual algebra. Next. For number 11, 3 kilogram mass on a silver spring oscillates 25 times in 80 seconds. What is the period of the spring pendulum? What is the frequency and what is the spring constant? So, N is 25, total time is 80. So period is total time divided by N, or 80 divided by 25. The frequency is the inverse of period, so 25 over 80. The spring constant, period, is 2 pi square root m over k. T squared is 4 pi squared m over k. K, 4 pi squared m over t squared. You've got your m, you've got your t. The m is mentioned as 3 kilograms. The fact that it's silver is irrelevant. And there you go. That's 11. Number 12, we have a simple pendulum. The mass is 3 kilograms. Doesn't really matter because it's a simple pendulum. It oscillates 45 times in 145 seconds. The period is total time over N. N is 45, total time 145. How long is the string? So T is 2 pi square root L over G. Looking for L, T squared, 4 pi squared, L over G. T squared G over 4 pi squared is equal to L. And that's the length. If the experiment is performed on the moon, what is the new period of the pendulum? Now that you've got your L, take that L and put it in there, and then you've got G prime, and that G prime is G over 6. And then you have your new period. All right, 13. You make 30 oscillations in 90 seconds. The distance between the peaks of the waves is 20 meters. What is the period of the wave? Well, period is total time divided by N. You've got total time 90, you've got N 30. Distance between the peaks of the waves is 20 meters. That means lambda is 20 meters. The lambda F is equal to velocity. So F is inverse period. So take whatever answer you get, invert it, and then multiply it by 20, and then that will give you the velocity. This was the last thing that we covered in lecture on Thursday. All right, last problem, number 14. Reminding everyone, if you take a look at Blackboard, I think I wrote 1400 as the correction. I'll accept either 1400 or whatever I wrote on that Blackboard. But it doesn't affect much in terms of the theory. This is a hybrid problem. This is one of those passage problems where you're having to bring in several topics of information about physics. You have, and I'm going to draw this a little bit bigger. You have the main axle. That is the rotation point. A half meter above on the wall is a string that goes from there to there. And I want to know what is the tension on the string. Now the distance from there to there is 0.5 meters. Now the tension on that string is up and to the left. There's going to be a tension in the Y at that location, and then a tension in the X in that location. The distance, 1.5 meters, that's 0.5. This whole distance is 2. Now, as far as the bar is concerned, there is a tension at the end pulling down, and we must find that tension. It won't be as simple as this mass hanging down at the end. M1 is 50. It's not as simple as 500 newtons. And why is that? It's because there's water, and that object, which has a density of 1,400 kilograms per cubic meter, is completely submerged in it. So we must find out what this T is. Let's focus only on this part. Let's find T for this submerged object. So there's my object, there's my tension, there's my M1G down. There is also a buoyant force up because it's completely submerged. Now the sum of the forces is equal to 0. This thing isn't popping up or going down. So T plus buoyant force minus M1G, that gives you everything that you need to know. So M1G minus buoyant force is equal to tension. M1G, 50. Well, actually, I'm going to write one more layer of algebra. Buoyant force, rho water, volume of displacement times gravity is equal to tension. I don't know the volume of the object, but mass over volume is density. So mass over density is equal to volume. M1G minus rho W, mass 1, rho, and then G is equal to T. So M1 50, 10 minus 1,050 times 10 divided by 1,400. And that gives you the new tension. $142.9 newtons. Double check. Yep, that's what I get.
In the first picture, it's the tension arrow pointing down, but in the second one, it's pointing up.
In here, we're considering only the forces acting on this object. This tension here, we're only considering the forces acting upon the bar.
But we're not worried about that, right?
Not yet.
For the problem.
Not yet. Now that I know that the tension here is 142.9, I now know that the tension there is 142.9.
Oh,
It's the same. Because otherwise the string would just rip itself apart or bunch up or do whatever. So now we know for a fact that this thing is not rotating about that point. And I'm going to call this x1 and this x2. So the sum of the torques is 0. There are two forces acting on this that are of any note. This one is going straight at the rotation point. It is not causing torque. So my two torques are Ty(x1) and Tx2. This one is to the right and up, out of the page positive. That one is to the right down, into the page negative. So Tx2, and I really should make it T of the end, because T is the T of the string. Or you could use H for hanging, it doesn't really matter. But make a difference because this is the T that I'm looking for.
Okay, so the tension we found earlier was not for the string.
That was for that string right there. The 142? Yeah. And so we get this. Now there is a relationship between Ty and T. This angle here is the same as that angle there. That theta is inverse tan of y over x1 y is 0.5, x1 is 1.5. So inverse tan of 1/3 18.4. 18.4 degrees. So the relationship also is sine theta is ty over t, or t sine theta is equal to ty. Substitute that into here. Te x2 x1 t sine theta. So now TE 142.9, X2 2, X1 1.5, sine 18.4. And that's it.
Okay, so how do you go from ty x1 to x1 t sine?
Oh,
Oh, okay.
you see it?
Yeah.
Just need to stand up. So you found the component of the tension in the Y from rotational equilibrium. And then you just had to identify what part of T is that Ty comes from. And it's just a couple of algebraic identities. All right, that's it. That's all I got. Bye bye. Bye bye.